Hi everybody, this is Luke D and this is Bio 2013 and today we're talking about carbohydrates. So one, I'm going to apologize for the glare here, but nothing really I can do about it, so I'm not going to worry about it. So where are carbs found? Carbs are found pretty much everywhere. You can find them in wood, you can find them in pasta, you can find them in sugar. All living things that I know of have carbs, and we eat them a lot. And there's a lot of debate surrounding carbs about whether they're good or bad for you. High fructose corn syrup, obesity, um, whether complex carbs are better for you than regular carbs. And we'll take a look at those things later. But first, let's just go ahead and take a look at the basic structure of carbs. Now, I want just to make a note that I expect you to be able to do this stuff on first glance. So I don't just go through and do this every time just so you can see it. Or sorry, I do this every time just so you can see it. So I expect you to be able to do this, like I said. I found an easy little shortcut. I right-clicked on the screen. I went to Style, Scheme, and then I'm just going to go to Ball and Stick. And that's going to do absolutely nothing unless you select all first. Style, Scheme, Ball and Stick. All right, so this is an example of a carb. One of the main ways we identify carbs is by how many carbons they have. So we look at this one, it's got 1, 2, 3, 4, 5, 6. Beyond that, it's got oxygens and hydrogens. And we know from the structure, from what we talked about before, that if you have a carbon next to an oxygen or a carbon next to a nitrogen, the carbon is going to be slightly positive, and the same goes for hydrogen. So if you have an oxygen or nitrogen next to a hydrogen, the hydrogen is going to be slightly positive. So you have basically a carbon chain with either a hydrogen or a hydroxyl group on the side of it. So that's going to make all the red things a little negative and all the gray and white things, except for these, a little positive. Which means that when you put this in water, all the positive and negatives from water are going to attract really well with this, and it's going to mix together nicely. So this is D-glucose. We're going to go ahead and put in some water. And we're just going to go ahead and start the simulation. I'm running on fast here. Turn on some hydrogen bonds. And then drop the temperature just a little bit. And you can see that everything sticks together really nicely. These oxygens are going to pair up with those hydrogens, and this molecule here, which is glucose, would dissolve really, really nicely in water. Hey, I realized I went over that molecular interaction kind of quickly, so I decided to jump in and show you again. So let's go ahead and stop this and zoom in. And then move this over just a little bit. Alright, so what you can see, now you can actually see this, is that the negative oxygen here, for example, is attracted to this hydrogen. It's also attracted to this hydrogen, and it's also attracted to that hydrogen. Oh, sorry. Let's see if we can turn that again. I don't know why I just made sound effects. It just seemed cooler. Again, negative oxygen, positive hydrogen. So this is going to mean that this molecule, glucose, is going to dissolve really, really well in water. The exception is going to be if I have like a gajillion of these glucoses, right? And this glucose has positives and negatives on its surface, so it can actually fold in on itself. Now, if it can fold in on itself, and we're not talking about just glucose, we're talking about thousands of glucoses put together. If it can fold in on itself, then and water can't get in between it, then it won't dissolve. It'll attract water, but it won't dissolve, and that's something that you see. It's kind of the reason that it's good for pooping, because it doesn't dissolve in water, but if you line your intestine with it, then it's slick because the water's still attracted to it, and so that's the real reason that things like fiber are good for you. So, hope that was informational. I'm going to take you back to the regular scheduled programming now. Bye. And it's also going to be very polar. So the exceptions to that are these kind of giant ones. Some carbs are really, really massive. For example, starch, glycogen, and cellulose. So let's go ahead and take a, oh, sorry. So all other carbs, this one, this one, this one, this one, are going to be pretty much polar, and they're going to be easily dissolved in water. You're going to see them both in this kind of line shape and then also in this ring shape. It does matter which one they are, so the shape of this molecule is very important. As a matter of fact, if you count up the number of carbons and hydrogens in this one and this one, you'll see that they're actually the same. But these guys act very differently. We saw receptor binding, so if this molecule, for example, were to bind to a receptor, you might see something like that. But if you have the same molecule or the same molecular formula, but in a line shape, it wouldn't work. So maybe we might need a receptor like that. They would fit together like that, and then my cyclic carb wouldn't bind. Okay, so let's go ahead and take a look at some more examples of carbs and where we use them. So these again are the examples of carbs that I just showed you, and you're going to have access to this. This is basically those big ones that I was talking to you about. So if you take glucose and you put a gajillion of them together, I don't actually know how many a gajillion is, but it's a lot. You'll put them together in this chain, and then you'll get starch. So these drawings of starch are actually all glucoses. So this little hexagon is a 6-carbon sugar. So what it's missing is each angle or each corner is actually a carbon, and it's missing the OH and the H that are coming off of it. So this is something that you're going to see a lot of. So you're going to see, you should pretty much, if you see this kind of hexagonal thing with nothing drawn off the sides, you should pretty much assume that that's going to be a carb. And I'll have to tell you otherwise if you don't, if it's something else. All right, we also have kind of like starch. You can see starch is a spiral. We have glycogen. So this is like that spiral, but it's got branches kind of coming off of it. So we call these secondary structures. When one structure folds into something, that's what we call a secondary structure. The primary structure of this thing is just repeating glucose elements. And then we have cellulose here. Cellulose is long chains of carbohydrates that are parallel to each other, and they attract each other, and they form fibers. So let's go ahead and talk about what you use starch for. Well, starch you use as, or plants use as a storage molecule. So it's going to turn out that a lot of times carbohydrates are going to be high energy molecules, and as a loose rule you can think of the number of carbons equaling the amount of energy. So starch, which has a ton of carbons in it, is going to have a lot of energy, and glucose, which has 6, is going to have considerably less. We actually store sugar in the form of glycogen. So in your muscles, place where sugar is used a lot, or any place that sugar is used a lot, you're going to have it stored in this form. That means that it won't act like a single sugar. So for example, if I were to test, if I were to put this in water and then test it for glucose, it would come up negative. It would come up positive for glycogen, and if I cut these bonds, then it would come up positive for glucose. But as of right now, this is a good way to store glucose without actually having it in the glucose form. The little cell wall thing that we see here in cellulose, it's actually pretty important. So here is what's called a scanning electron micrograph, basically really powerful microscope, and looking at bamboo cells. So this kind of smooth surface here is actually called a cell wall, and under it is what we use, what we know as the cell membrane. If you zoom into it really, really tight, then you'll see that these fibers, you can kind of see these fibers forming, and this is the cell wall, and again, this is cellulose, what you see here. Another kind of important reason you see carbohydrates around is you see them attached to proteins. So this is a cell membrane. This is what we call the surface of our cells. And if you look here, a lot of people think that the surface of a cell is actually smooth, but it's not. There's like these hair-like things that come off of it a lot. And those are a lot of times carbohydrates, these green things here, attached to a protein. And those help to identify the cell as your cell. So this is basically your flag. So when you have a cell, one of your cells, white blood cells, that is trying to destroy things, it won't destroy things with this tag. Those are called proteoglycans, and this is actually really interesting here. You can actually take out bacteria like anthrax just by clipping some of those carbs on the surface. Okay, so where would we find this in a cell? All right, so let's take a look. We're going to look at one basic cell here, and this is a neuron. Neurons are shaped a little funny, but what we're going to see is that glucose is going to be found in a few places, or carbs are going to be found in a few places. Like I said, they're going to be on the cell membrane, and I kind of drew this, and it looks horrible, but all right, so this would be, for example, our proteoglycan. It's got the protein part here and the carbohydrate part here, so this would be one of thousands and thousands of these things on the cell surface. You're also going to find it throughout the cell. So you're going to find glucose throughout the cell here. And you're going to find it specifically next to these little organelles, and an organelle is just like a functional, kind of like an organ in a cell. There's no real good definition for it, but you're going to find that in our cells we have these basically other organisms that are called mitochondria, and they have their own genome, and they move and they replicate within us, but they also help to break down carbs for a lot of energy. So if we just try to break down carbs without these mitochondria, we don't get that much energy. So we get something like 15 to 20 times the amount of energy if we have the mitochondria break down the carbs for us. So how these things work within us, within our cells, is actually really important, but not really that well understood. For example, I think they just figured out how the sugar gets in there. That's not exciting to you at all. All right, so talked about that. I guess let's talk a little bit about the debate that's going on about sugar. So let's just go ahead and Google fructose. And let's go ahead and look in the news for it. Okay, so we've got high fructose. Hunt manages to sneak high fructose corn syrup back into its ketchup, I'm guessing. Dr. Oz. So there's one thing I want to point out really quickly, and that is, if you have fructose, it doesn't matter if it's from like Kill Baby Corporation. Even if it's from a horrible place, if it's fructose, it's just fructose. So fructose from, Hunt's or from high fructose corn syrup is the same exact sugar as fructose from an orange, and it acts the same. So I just thought I'd point that out. But basically, there's a lot of questioning going on about obesity in America, and sugar is at a lot of the heart of that. So one thing I want you to know is you never, ever, ever look for real information in the news. The news is not a good place to look. The better place to look is a place called PubMed. So if you type in pubmed.gov, this is actually a Google for all the research that's done in the US that is funded by federal grants. So you can find the actual data and the actual experiments of anybody who ran any experiment in the US with federal money, assuming they figured something out. So if we type in fructose, no, so let's try this. So I actually came up with a couple links here. So the question basically is fructose any better for you or worse for you than sugar, other sugars? So if you, for example, ate the same amount of fructose and the same amount of glucose, would you become obese in one case and not in the other? And if you read this over, Matthias Schopp, the guy who wrote this, he actually says that if you take fructose and you give fructose preferentially to overweight adults, and you give that over, for example, glucose, and the people that are taking the fructose will actually have more fat in the front of them. But if you look at this study, and you can read this, you can view all this. This one suggests that it really doesn't make a difference whether it's fructose or glucose. You basically have the same effect, and one's not worse than the other. I happen to know this guy, and I happen to know that he does really, really good work, and he's one of the top kind of sugar guys around. So I'm going to trust him. And I also know he's done this on mice a million times, and he's gotten it to work. So there's a lot of debate surrounding sugar right now. Don't trust the news for the answers to that debate. You have to go to PubMed, and we're going to start doing that more and more so that you learn how to actually get to the truth of information. For right now, if you go to PubMed and you search anything, I don't know, brain transplant. I wouldn't try to go to anything beyond what's called the abstract. So the abstract is this part. It's generally going to be at the beginning of the paper. It's pretty much the simplest way, it's the simplest version of it, of the paper. So for example, I wouldn't read anything past here. And I would skip all the words that I didn't understand. So you're not going to understand a lot of them. Don't worry about that. Anyway, that's pretty much it for carbs. Let's see. Carbs have oxygens and hydrogens in addition to carbons. And the oxygens are slightly negative. They're big as far as energy storage. They also do a lot of other things. One of them is kind of tag the outside of the cell and help you to identify it. The number of carbons is loosely proportional to the amount of energy that they have, and they form secondary structures. You store energy in the form of glycogen and fat. Fat is not a carb. And plants store it in starch. And then you have cellulose, which plants also use, and that's structural. So that's it, I think. I hope I didn't miss anything. I hope you understood that. Have a great day.